Hello stat students, hope you're well today. Today we're going to look at section 5.2. It's the addition rule and complements rule for probabilities. Again, just like yesterday, there may be some new names in here, but the concepts are all things that you would have seen before. So the objectives that we'll be covering in section 5.2 are using the addition rule for disjoint events. We'll be looking at the general addition rule, and we'll also be computing the probability of an event using the complement rule. And again, there may be some terminology there that you're unfamiliar with, but this is going to be familiar material once we get rolling. Objective 1, using the addition rule for disjoint events. Two events are disjoint. This is an important concept for you to understand. Two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. Okay, so events that can't happen at the same time. So a good example of that would be flipping a coin. The possible events, the sample space, if we're using stats language for flipping a coin, is heads or tails. It's impossible to get heads and tails on the same flip, and so those two events are mutually exclusive. They're disjointed. Okay, so there's no possibility of flipping a coin and getting heads and tails. So the events are mutually exclusive or disjointed events. Okay, here's a picture of what a disjointed event looks like. Let's skip the words here and look down at the figure at the bottom here. We have this is our sample space. So our sample space is all the digits from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So all of the digits are available there, and they are divided into different subsets. So we have E, which is 0, 1, and 2. F is 8 and 9, and then the 3, 4, 5, 6, 7 are digits that are in S, but not in E or F. The important thing is to note that all three of these sets are disjoint. In other words, they have no events in common. Okay, so we're going to look up here, back into the words now, and see what we're doing. It says, for example, suppose we randomly select a chip from a bag where each chip in the bag is labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's the bag, the sample space. Let E represent the event that we choose a number less than or equal to 2, and let F represent the event that we choose a number greater than or equal to 8. So that's F and E as shown below. The events are disjointed because they have no, E and F have no events in common. Okay, so using this, let's have a look at the probability of getting an element of E, and that's, again, we're back to the simple probability. It's the number of elements in E divided by the total number of elements in the sample space, or 3 out of 10. Okay, and if we looked at the probability of getting a value from F, it's the number of values in the sample space of F, and divided by the number of in the set F, divided by the number in the sample space, so 2 out of 10 was 0.2. Now, if we wanted to talk about the probability of getting a value that's in either E or F, right? This is where we're headed with this, E or F, that's the union of these two sets, anything in this set or anything in this set. It's the number of the values in E or F divided by the total number of values, or 5 out of 10. Now, what they want us to reduce at this point is that the probability of E or F is equal to the probability of E plus the probability of F. We get 0.5. So that is the rule that we will use for disjointed events. If we have events that are disjointed or mutually exclusive, the probability of the union of those two things is going to be the sum of the probabilities. So if we write it in mathematical notation, the probability of E or F is simply the probability of E plus the probability of F, but only if the events are disjointed or mutually exclusive. Okay? Now this property is also going to extend to more than two sets. If we had 3 or 4 sets or more that are disjoint, then the probability of the union of those sets is just going to be equal to, probability of the union of all the sets is equal to the sum of the probabilities. This is a graphical error there. Okay? Should be ... All right, that's the addition rule for disjoint events. Okay, so here's what that might look like in a real problem. It says the probability model to the right shows the distribution of the number of rooms and housing units in the United States. Okay, so we have a probability distribution, or we're being told here, first of all, to verify that it's a probability distribution or probability model. So we need to go back to our 5.1 conditions for it being a probability model. All of the probabilities have to be between 0 and 1, and we're good there, right? All of these probabilities are greater than or equal to 0, less than or equal to 1. And the sum of the probabilities, this would need a little work, the sum of all these probabilities has to equal 1. And if we took the time to do the arithmetic, then we would see that the probabilities do add up to 1. All probabilities are between 0 and 1. And that verifies or confirms that this is indeed a valid probability model. Okay, and letter B says, what is the probability of randomly selecting a housing unit that has 2 or 3 rooms? Now, they're telling us here that these are disjoint events. Like, we're kind of given that they're disjoint, but let's take a moment to determine why. Because if we're going to use the probability rule of simply adding the probabilities, we have to confirm that the events have no overlap. So could a 5-room housing unit also be a 2-room housing unit? The answer to that question is no. It's one or the other. It can't be both, which confirms that we have a disjointed scenario taking place here. Okay, so the probability that a housing unit has 2 or 3, okay, the probability of 2 or 3, because they're disjointed events, is the probability of 2 plus the probability of 3, which is equal to these two values, 0.32, 0.093, and that gives us 0.125. So the probability that a housing unit has 2 or 3 rooms is equal to the sum of those two probabilities. Okay, so the probability of a housing unit, letter C, if we'll move on to letter C, probability of selecting a housing unit that has 1, 2, or 3 rooms is simply going to be the sum of these 3 probabilities, 1, 2, or 3 there, and if you add those together, 2 or 3 is already 0.125, so adding 0.1 to that is going to give us 0.135 as a probability of 1, 2, or 3. So again, if we have disjointed events, then the probability of the union of those disjoint events is going to be the sum of the probabilities. So just add up the individual probabilities to get the union of the probabilities. All right, so objective 2 is to use the general addition rule, which is very, very similar. But the general addition rule applies whether E and F are mutually exclusive or not. Okay, so let's talk about this. The probability of E or F for any two events. Any two events. That they don't have to be mutually exclusive. Now let's make some sense of this. The probability of E or F is still going to involve the sum of the individual probabilities, but then we're going to have to subtract the probability of E and F, so we're subtracting the intersection. All right. So if the two sets have values in common, if E and F have values in common, and we simply add those two things, then we're counting some values twice. Which values are we counting twice? We're counting the values that are in E and F. So we have to subtract that away, so we're only counting things one time in our probabilities. So we take away the intersection, and this next example is a really good look at what that entails. All right, so suppose that a pair of dice are thrown. Okay, we got a pair of dice. We got all the possibility. There are 6 columns and 6 rows, so there's 36 total possibilities here. Need to get familiar with that number because that's going to be useful to us moving forward. Let E be defined as the event that the first die is a 2, and let F equal the set such that the sum of the device is less than or equal to 5. So if you add the two die together, you get something that is less than or equal to 5. So let's identify these two sets that they've given us here. E is that the first die is a 2. Now that's going to be all of these values right here. Okay, they've got them nice and organized for us so that that's all of the outcomes that are in set E. Okay, set F is that the sum is less than or equal to 5. Now this is also going to be pretty easy for us to identify. The sum is less than or equal to 5. If we start here, we've got a sum of 2, a sum of 3, a sum of 4, a sum of 5. If we went any further that way, it's going to cut off. So we got these that will work, and then it looks like we got to come over here, come down there, because those values right there is 5, and on the other side it's a 6. Okay, and then it looks like we're going to come down again, catch that 3 and the 2. You know, this 3 and the 3 is 6, so we can't use those. And then we've got that pattern kind of continues. We come over here and pull down and catch that 1 and the 4. And that's set right there. If I kind of color that in a little better, let me use a highlighter. If I color that set in a little better, then we can kind of see the set F is all of those values. All right, so you can see here already that we've got 3 things, right? These 3 things right there, right, are in both sets. They're in set F and in set E. So that's the intersection that if we're not careful, we're going to count twice. But let's just use the rule that we have here. Probability of E or F is equal to, this probability is equal to probability of E plus the probability of F minus the probability of the intersection of E and F. And I'm going to use the intersection symbol there, even though we haven't talked a whole lot about that. E intersect with F. Okay, so the probability of E, now E is this square box right here, the square box that goes all the way across. There are 1, 2, 3, 4, 5, 6 outcomes out of 36 in E. So 6 out of 36 is what we're looking at there. 6 out of 36 is the probability of E. The probability of F, that's all of these things in this box here. There are, right, that's F. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values, 10 out of 36 values in F. And as you can see, as I just went through there and counted it, we counted those 3 values right here. We counted these 3 values right there, these 3 values. We counted those 3 values twice. And so to keep from counting them twice, we have to subtract the intersection of E and F, the values that they have in common. So we're going to take away the probability of E and F, and then it's going to look like this. So we're going to have probability of E is 6 out of 36, right? We just counted those. 6 out of 36 is the probability of E. Probability of F is 10 out of 36. The probability of the intersection of E and F is 3 out of 36. And so if we just follow our formula here, you get 6 out of 36 plus 10 out of 36 minus 3 out of 36, which is 13 out of 36. And you can definitely see an advantage of not simplifying along the way if we just keep the unsimplified values rather than using these values. When we're adding fractions, leaving the common denominator is going to be helpful to us. So the probability of rolling 2 die and having the first die be a 2 or the sum less than or equal to 5 is 13 out of 36. All right, so thirdly, our third objective, and this one's even a little more simple than the other two, if you can believe that, is dealing with the complement of an event. So if we let S denote the sample space of a probability of an experiment, and let E denote an event, the complement denoted EC, or we're just going to call this, we're not going to call this EC, we're going to call that E complement. Right? That's how you read that notation. Is all of the outcomes in the sample space that are not in the event E. Okay, so if we talk about the probability, or not if E, if we're talking about heads or tails again, flipping a coin, if we're flipping a coin, all right, E is tails, then E complement would have to be what? All right, hopefully all of you immediately say heads. Okay, so that's what we mean by the complement of an event. Now, it's a little bit more complicated if we were talking about rolling a die, right? Rolling, not polling. Rolling a die. We've got, what are the options? If E is 1 or 2, right? Rolling our die, then E complement would be what? E complement would be the remaining options, 3, 4, 5, or 6. Okay, so that's just how, what we're doing here is getting our definition for complement. Now, this rule is extremely important. The complement rule, if E represents any event and E complement represents the complement of E, then the probability of E complement is equal to 1 minus the probability of E. Now, here's what this means if we just kind of look at this. If we added E, probability of E to both sides, then here's what we get. The probability of an event and not the event is always going to equal up to 1, right? So it's just like the probability of heads, tails, right? It's always equal to 1 because that's all outcomes. So this, that you could work this around and do a little bit different. Now let's talk about how this may be useful. This is just a pictorial thing. The entire region is our sample space S, right? S is made up of this event and things that aren't in the event. And the probability of all of those things has to add up to 1. And so that's where you get this formula from, okay? All right, so how does this work? According to the American Veterinary Medical Association, 31.6% of American households own a dog. What's the probability that a randomly selected household does not own a dog? So we're talking about owning a dog, and the complement is not owning a dog, okay? And then hopefully this is pretty obvious to you. The probability of not owning a dog, oops, I didn't have that, the probability of no dog is equal to 1 minus the probability of the household having a dog. And so that is 1 minus 31.6%, which is going to be, actually I should have done 100 if I'm going to speak in percents here, 68.4%, is that right? Yeah, I think that's right. 68.4% is the probability that it does not own a dog. So it's just 1 minus the complement. Now, this is really simple and intuitive at this level. It becomes really helpful when we start doing cumulative probabilities, and this is going to be an example of how it could work for us. So the data to the right represents the travel time to work for residents of Hartford County, Connecticut. Now, this is a frequency distribution, right? It's not a relative frequency distribution. When we're finding probabilities, we want to use relative frequencies, so we've got to kind of go back to Chapter 2 and determine how we are going to convert these frequencies to relative frequencies. But we're not going to have to do all of these. Let's look at what we could do to answer these questions. So letter A says, what is the probability that a randomly selected resident has a travel time of 90 minutes or more? Okay, 90 minutes or more, that's this group of people right down here at the bottom. There's 4,895 people in that county that have a travel time of 90 minutes or more. So to find the probability, we would need to do 4,895 divided by the total number of people, which is the sum of that column. And I think they're going to give us that value here. There's a total of 393,186 people in the county. And so the probability that a randomly selected resident will have a commute time of 90 or more minutes is 4,895 out of 393,186, or 0.012 probability. Okay. Now, we've not referenced any complements yet, but here's the other side of that. Here's where that's useful. Okay, compute the probability that a randomly selected resident of Hartford, Connecticut will commute less than 90 minutes. Now, if we went back to our chart and we wanted to do this using individual probabilities, then we could either do the sum of all of these divided by the total number, or we would have to convert these frequencies to relative frequencies and then add all of these probabilities together to determine. But using the complement makes much more sense. Okay, if only 0.012 people spend 90 minutes or more, then what are we interested in here? We're interested in the people whose commute time is less than 90 minutes. It's the complement, right? That includes everybody. People who takes 90 minutes or more, people who take less than 90 minutes, that's everybody. So the probability of 90 minutes is equal to 1 minus the probability of 90 minutes or more. Less than 90 minutes is 1 minus the probability of 90 minutes or more, and we get a probability of 0.988. So that's how complements are going to be most useful to us. So that's it for 5.2. And your homework for this section is to page 254, 1 through 6, and following there. And you need to turn this in on Power School Learning. There's an assignment tab created or assignment created for this, so you can upload a PDF of your work. And I can see that you do it. And if you have any questions, you can post that in the discussion forum that is created for section 5.2, or you can shoot me a message via phone or through Remind. Hope you guys are doing great. Looking forward to seeing you again soon. Have a great day.